Hello friends, welcome back to my YouTube channel. Today I'm going to continue my discussion on simple distillation. So this is part 12 of my discussion on distillation, and today I'll be discussing a numerical that is based on simple distillation. In my previous video I have discussed the concept of simple distillation. For those of you who have not yet seen that video, I'm giving link to that video in the description section. So today, let us understand or let us learn how to solve uh, a numerical that is based on simple distillation. So you must be remembering, those who have watched the video, you must be remembering that the governing equation for simple distillation is Rayleigh's equation, and how to solve it I have discussed in my earlier video. So let us use it for solving a numerical in the present video. So let me first tell you what is the numerical statement. So you have 120 moles of benzene and toluene solution containing 45% mole of benzene is subjected to a differential distillation at 1 atmosphere pressure. At the end of the operation, the composition of benzene in the residue is 29% mole. Calculate the total moles of mixture distilled. In this case, benzene is the more volatile component and average value of the relative volatility is 2.16. Okay, so you have 120 moles of benzene and toluene solution, which is containing 45% mole of benzene, and it is subjected to a differential distillation. Differential distillation, as you know, is the other name of simple distillation. So that the solution is subjected to a differential distillation at 1 atmosphere pressure. At the end of the operation, the composition of benzene in the residue is 29% mole. Calculate the total moles of the mixture distilled. In this case, benzene is the more volatile component, that is, out of benzene and toluene, benzene has less boiling point and more vapor pressure, so that's why benzene is the more volatile component, and average value of the relative volatility is given for the solution, it is 2.16. Okay, so let us continue. So let us first note what are the given things in this numerical. So the feed solution in this case is a solution of benzene, and let me denote it by A, and toluene, let us denote it by B. So you have a solution, a liquid solution of benzene that is A, and toluene that is B. The quantity of the feed solution is given to us. The quantity of feed solution is 120 moles. Benzene is the more volatile component again, and in the feed solution there are 45% mole of benzene in the feed. That means from this information, what is important information we can collect. One is F is 120 moles, and second is XF is 0.45. Okay, so for feed solution, the quantity is known to us, that is, it is 120 moles, and the composition of more volatile or more percent of more volatile component is known to us, it is 45, and if you convert it to fractions, it will be 0.45. Okay, So let us continue. Then further, what is the process? This feed solution is to be distilled, differentially distilled. It should be distilled by using simple distillation or differential distillation. The pressure for the operation is 1 atmosphere. At the end of the operation, the residue is to contain 29% mole of benzene. So from this information, what we can note? We can note that pressure is 1 atmosphere and XW, that is composition of the residue, mole percent of more volatile component in the residue is given to us. It is 29%. So from that, we will note XW as 0.29. So if it is 29 mole percent, mole fraction will be 0.29. Okay. Further, uh, is any other parameter given to us? The answer is yes. It is the relative volatility. Relative volatility is given to us. The relative volatility is 2.16. That is alpha AB is 2.16. And what is the objective? The objective is to find the total moles of the feed solution that gets distilled. So that means we have to get D moles of distillate that are obtained during this process. Okay, so these are the given things. And now let us solve it. Let us look at the solution to the numerical. What will be the approach for solving this? So we are going to obtain D, that is moles of the feed solution that are distilled. D will be obtained by using the following equation. What is the equation? The equation is total material balance. The feed solution will be either converted to distillate or residue. F is given to us, it is 120 moles, and W we need to calculate it, and W we are going to calculate by using Rayleigh's equation, which we have already know. What is the equation? The equation is ln of F by W, that is equal to integration of dx upon y minus x from xw to xf. So with xw known, after using this equation, we are going to get xw is given to us. With xw known, the integral on the right hand side, that is this integral, we are going to solve it graphically. So for that, we will be plotting a graph of x on x-axis and 1 upon y minus x on y-axis, and the area under the resulting curve is then measured between the limits xw and xf, and that area is nothing but the integral. The measured area is the value of the integral on the right hand side, that is this integral. Okay, so in this way, once you get the value of the integral, so you have ln of f by w is equal to some known value. F is known, and then you can easily solve the equation to get the value of w. Okay, what steps? Once we know what approach is to be followed, now let us list the steps that we need to follow to solve this numerical. So first, since we have to plot the graph, we need the Weber liquid equilibrium data, that is VLE data, XY data. That is not given to us. So we need to have it, or we need to generate it. In some cases, in this data may be directly given to you, so you can skip this step in that case. But here data is not given to us. Instead of that, they have given relative volatility to us, so we are going to use the relative volatility to get the VLE data. Okay, after we have generated the VLE data, we are going to plot it. We are going to plot the required graph, x versus 1 upon y minus x, and then we are going to find area under the curve. Okay, once area is known, that means the integral on the right hand side of Rayleigh's equation is known to us, we are going to calculate w. and then after calculating W by using total material balance, we are going to calculate D, and that is the objective. So first let us follow all the steps. First, the step we need to generate the VLE data. So this data, vapor liquid equilibrium data or XY data, it is generated by using this equation. You know this equation, y is equal to alpha abx divided by 1 plus alpha ab minus 1 into x. So if you remember, if you have seen my earlier videos, you know how to use this equation and how this equation is obtained. Okay. So what we are going to do, we are going to select different values of x. What values of x? Those values that lie between 0 and 1. Now why 0 and 1? Because x being mole fraction, it can have a minimum value of 0 and a maximum value of 1. It cannot be less than 0 and more than 1. So the limits are 0 and 1. Okay. So after selecting different values between 0 and 1, we are going to calculate the corresponding values of y by using this equations. So you have different values of x that you select, and then you have corresponding different values of y that you calculate by using this equation. Okay, so let us move it. Continuing with the step, I'm just again writing the equation that we are going to use. Equation is y is equal to alpha abx divided by 1 plus alpha ab minus 1 into x. What values of x are selected? 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9 and 1. Okay, so you can have different values between 0 and 1. It is up to you. So for example, you could have 0.01, 0.02, so on and so forth. But selecting the values that I have shown, it is the easiest way of doing the task. Okay? So different values of x lying between 0 and 1. These are the values that we have selected. And we are going to calculate y by using this equation. Alpha AB is given to us, it is 2.16. Now let us check what will be the value at x is equal to 0. At x is equal to 0, y will also be equal to 0. So that is 2.16 into 0 divided by 1 plus 2.16 minus 1 into 0. So I have used x is equal to 0 in this equation, and alpha AB is equal to 2.16. So this will be 0 upon 1 plus 1.16 into 0, that is 0 upon 1, that is 0. Okay, one more value I will show you how to get y at x is equal to 0.1. So at x is equal to 0.1, if you use the equation, it will be y is equal to 2.16 into 0.1 divided by 1 plus 2.16 minus 1 into 0.1, that is 0.216 divided by 1 plus 1.16 into 0.1, that is 0.216 divided by 1.116, that comes out to be 0.19. Okay. So similarly, for every value of x that we have selected, we are going to calculate the corresponding value of y. So now you can do the calculations. I'll directly show other values of y. So similarly, values of y for remaining values of x, they are calculated. So now let us understand how it is done. Okay. So now I'll show you all the values. So you have different values of x: 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9 and 1. Okay, and corresponding y values, we have seen how it is 0 for x is equal to 0, for 0.1 it is 0.19, for 0.2 it is 0.35, 0.3 it is 0.48, for 0.4 it is 0.59, 0.5, it is 0.68, 0.6, 0.76. For 0.7 it is 0.83, 0.8 it is 0.9, and for 0.9 it is 0.95. And finally you can check when x is equal to 1, y also is equal to 1. Okay, so once xy data is ready with us, that completes step number 1. Now let us go to the next step. What is the next step? The next step is plotting of the required graph. Okay, so we are going to plot x on x-axis and 1 minus y, 1 upon y minus x on y-axis. Okay, so uh, from the generated BLE data, that is uh, from the data that we have obtained, first we need to get this value, because we are going to plot 1 upon y minus x. So we need to get values of this term. For this term 1 upon y minus x. Okay, that is also a task. Then once that is obtained, then you can go for plotting the graph. Okay, then after plotting the graph, you are going to measure the area under the curve between the limits xw and xf. Okay, now let us see. So we already have these values. Again, I'm just showing you those values, x and y values. Now we want 1 upon y minus x values. So I'll use another table for that. So y minus x. So I'll subtract x from each y, and I'll be getting the corresponding values. And then once I get y minus x, I'll be getting 1 upon y minus x. Okay, so y minus x will be this value minus this value. 0 minus 0 is 0. Then 0.19 minus 0.1 is 0.09. 0.35 minus 0.2 is 0.15. 0.48 minus 0.3 is 0.18. 0.59 minus 0.4 is 0.19. 0.68 minus 0.5 is 0.16. 0.76 minus 0.6 is 0.16. 0.7 minus 0.83 is 0.13. 0.9 minus 0.8 is 0.1. 0.95 minus 0.9 is 0.05, and 1 minus 1 is 0. Okay, then let us get 1 upon y minus x values. So 0 upon 1 upon 0 is infinity. 1 upon 0.09 is 11.11. 1 upon 0.15 is 6.67. 1 upon 0.18 is 5.56. 1 upon 0.19 is 5.26. 1 upon 0.18 is 5.56. 1 upon 0.16 is 6.25. 0 upon 1 upon 0.13 is 7.69. 1 upon 0.1 is 10. 1 upon 0.05 is 20, and 1 upon 0 again it is infinity. Okay, now we have got all these values of 1 minus x. Now our task is we are going to plot x on x-axis and 1 upon y minus x on the y-axis. Okay, so let us do. Okay, so let us plot the graph. So on x-axis we are going to plot x, and on y-axis we are going to plot 1 upon y minus x. So on x-axis we are going to plot x, whereas on y-axis we are going to plot 1 upon y minus x. So if we have the data, if you plot the values, you'll be getting a curve. You'll be getting a curve like this. Okay. Then after getting the curve, our next task is to find the area under the curve. So for that we need to use these limits. One limit is xf is, the other limit is xw. Okay, so xf, let us locate it on the graph. So xf on the graph is over here, so I'll use that limit, and the other limit is xw, which is 0.29. So 0.29 is over here. Okay, so we need to measure this area, the area that lies within this region. Okay, so now what I will do, I will just count the number of small squares, small blocks, you can say, the small block. I'm showing you the small block. My task is, what I have decided, I have decided to count such blocks that lie within this region, and then by knowing area of that block and number of blocks under this in this region, I'll be getting the area under the curve. Okay, now let us find out area of this block. Okay, so on x-axis the scale is 1 centimeter is equal to 0.1. That means on x-axis this distance will be 0.1 divided by 5. Okay, so there are 5 small divisions, so it will be 0.1 divided by 5, and that comes out to be 0.02. Okay, whereas on y-axis this distance is equal to 1, so area for this block will be 1 into 0.02, that is 0.02. Okay, so I have shown the calculation. Area of small block or small square, it is 0.02, the dimension on x-axis, and 1 which is the dimension on y-axis. So area of one small square is 0.02 into 1, which is nothing but 0.02. Are you understanding it? Why 0.02? Because from 0 to 0.1 there are 5 small divisions, so length of one division will be 0.1 divided by 5, which is 0.02. Okay, so area of one small block, it comes out to be 0.02. Okay, the number of small blocks, you just count it, count those blocks. So for example, this line is dividing this distance into 2, so this will be half of the block, so half plus half plus half plus half, that is 2, and plus half, 2.5. Similarly on this side you have 2.5. Okay, then if you count all the blocks, and then there is some area that is lying above 5 below the curve. Okay, so if you count those blocks, the number of blocks for me, they come out to be 42.25. so I have got 5 lying within this region, 2.5 lying within this region, and then another 2.5 lying within this region, so that is total 5. And then I have calculated all the remaining blocks, so that comes out to be 42.25. You can calculate it, you can check it. Okay, the idea is you need to calculate you need to count the number of small blocks. So number of small blocks into area of each block will give you total area under the curve between the limits xw and xf. Okay, now let us do that calculation. Okay, so now let us do the calculation. Okay, now from the previous slide we have found out, we know area of one small square, it is 0.02. We have counted the number of such small squares between the limits, so that is 42.25. let me check, this is not 31.75, it is 42.25. Okay, so therefore total area under the curve between the limits, it will be n into a, that is 42.25 into 0.02, that comes out to be 0.845. so area under the curve between the limits xf and xw, it is 0.45. That is that this is nothing but the value of the integral, so integral dx upon y minus x from xw to xf is now 0.845. Okay. Now let us use the Rayleigh's equation. We have got the integral, but according to Rayleigh's equation, this integration from xw to xf dx upon y minus x is equal to ln of f by w. We now know what the value of integral. So you have ln of f by w is equal to 0.845. F is known to us, it is 120 moles. So ln of 120 by w is equal to 0.845. That is 120 by w is equal to e raised to 0.845. E raised to 0.845 is 2.33. So therefore 120 by w is 2.33. That is 120 by 2.33 is equal to w. That is w is equal to 51.50 moles. Okay. So in this way, by plotting the graph, by measuring the area under the curve, we have got the value of w. Now the only remaining task is to get d. So for that we are going to use the total material balance. Total material balance is F is equal to d plus w. F is known, w we calculated. So 120 is equal to d plus 51.50. That gives us d is equal to 120 minus 51.50, which comes out to be 68.50 moles. Okay. So we have achieved the objective. Therefore, the total moles of the feed solution that gets distilled are 68.50. Okay. So in this way, you can solve numericals where you'll be getting the integral in the Rayleigh's equation by plotting a graph. Okay. So I hope you have understood how to solve such numericals, and I will solve one or two more numericals, or in my coming videos I will tell you how to solve the same numerical by other ways. One is, first we will solve the integral analytically, and then we will also know how to solve the integral numerically by using a suitable numerical method. Okay, that's it for today. Thank you for being with me. I hope you have understood the numerical, how to solve numericals, the present numerical. If you have any doubts, you please mention them in the description section. Thanks for being with me. Do subscribe to my channel. Ask your tell your friends to subscribe to my channel, and continuing watching my videos on different aspects of chemical engineering. Thank you. Have a nice day. Bye.